Hello, this is Ms. DB, and we're going to continue with Chapter 12 on Section 2 on translations. Our objective is to identify and draw translations. A translation is a transformation where all the points of a figure are moved the same distance in the same direction. A translation is an isometry, so the image of the translated figure is congruent to the pre-image. A translation example in real world is when we move the couch over, when we slide the book across the table. Those are translations. The first part of your worksheet is you are just going to say yes or no whether or not these appear to be translations. If not, explain why, or if you know what they would be called, write that. So in A, a translation does not flip a figure over a line. That's called a reflection. So A looks more like a reflection. But B, if we took the blue figure and slid it in this direction, it looks like that would be a translation. And this is just some more examples. A looks like a translation to me. It looks like it goes to the right and then up. B, though, I don't think those triangles are the exact same size. And a translation is an isometry, which means that the shape, the original figure, the pre-image, has to be exact same shape and size as the image. A translation uses a vector. So it's a transformation along a vector, and we learned about vectors this year, such that each segment joining a point and its image have the same length as the vector, and it's also parallel to the vector. So from A to A prime will be the same distance as the vector's length, and it'll be parallel to the vector. Again, you don't have to copy from a worksheet, but it says to draw the translation along V. So they want us to take this quadrilateral, this blue quadrilateral, and move it in the same direction and by the same length as this vector. So you would get a ruler and you would measure how long. Let's say that this is 1, 2, 3 centimeters. So that means we would take every point here and we would move it 3 centimeters, 1, 2, 3, in the same parallel direction as the vector. So I'm going to go ahead and let them show the nice parallel lines. There's the parallel lines through every vertice, and then you would have to measure. And then you make your new points. That would be, if this is 3 centimeters, 1, 2, 3, then every vertice needs to be 3 centimeters from the vertice on the pre-image. And then you connect your points, and then that is your new translation. Again, this is difficult to do online. If you don't have a scanner or a digital picture, it's hard to show me this, but we will be doing the coordinate translations, where we'll be on a coordinate system. This is just another example showing what you would do. You would draw the parallel lines, then you would measure the length of the vector, and on those parallel lines you would make your points of your image, and then you would connect them. A vector in the coordinate plane is written with these pointy brackets. On our keyboard we'll use the less than and greater than signs, where A is the horizontal change and B is the vertical change from the initial point to the terminal point. Don't confuse that with a coordinate on a coordinate system. It's a vector. Okay, in the coordinate plane, here's how we will translate things along a vector. If we have a point x, y, and we are translating it along the vector, the horizontal change is A and the vertical change is 0, then we will add A to our x coordinate and our y coordinate would stay the same. So you just add A plus our x coordinate together to get to our image point. For a vertical translation, the x stays the same, the x coordinate stays the same, the y coordinate changes by you will add whatever the vector vertical distance is. And if you have a translation along a vector where both a and b have a value, both the horizontal and the vertical, then you need to add the horizontal to x and the vertical to y. All right, let's do a problem. So we are going to translate a triangle with the given vertices, it's D, E, F, along the vector with the horizontal component of 3 and a vertical component of -1. So every point really will move to the right 3 units. This is another way of saying it. Right 3 and up -1. Well, up -1 is the same as down 1. You may want to think about it that way. So that's what's going to happen. All right, so we are going to start. Well, I would start by sketching it. Sketch. So I would put my original, I think I'll make my original blue. The original is called the pre-image, so we want to point at -3, -1, that's D. We want to point at E is 5, 3, 1, 2, 3, 4, 5, and up 1, 2, 3. And F is at -2, -2. That's F. So if we connected this, we would get a triangle. And then we are going to translate it along a vector that goes from a horizontal component of 3 and a vertical component of -1. Let me draw that vector. Let's say that my terminal point was at 0, 0 of my vector. And I would go 1, 2, 3, whoops, and down 1. So my vector is like that. So that means that every point needs to move in a way that's parallel to my vector and is that long. The way to do that algebraically or mathematically is you add 3 to the x-coordinates and you subtract 1 from the y-coordinates. So we're going to subtract 3 from 5 and get, oh, which one are we doing first? D first, sorry. Subtract 3 from -3 and you get 0. -3, actually we're adding 3, sorry. -3 plus 3 is 0, and -1 minus 1 is -2. So there's our new point for D. Let's make that red. You can make the points as you go, or you can wait till you find all of them. So D is at 0, -2. Here's my D prime, which is after the translation, so this is called the image. Then we do the same thing for E, which was 5, -3, and we're adding 3 to the x-coordinate and subtracting 1 from the y-coordinate. So our new point is at 8, 1, 2, 3, 4, 5, 6, 7, 8. My E is going to be off of the screen, but it's going to be approximately, over here, but pretend that that's moved over a little bit because I didn't think ahead to how big my graph would need to be. And then finally my F prime will be at 1, -3. So when you connect these, picture my E prime as being a little bit farther away. Your new triangle has moved to the right 3, just like we thought it should, and down 1. Now their graph is going to be better because my graph I accidentally didn't plan ahead as well as I should. Did I graph mine incorrectly? Apparently. Can I go back and see my lines, or are they gone? Because I must have graphed, I had a point at, did I go 5 up 3 instead of 5 down 3? Or is it just that there's, no, mine looked different. I must have done 5 +3 instead of 5 -3. and I erased it now, so I can't go back and look at my mistake, but try not to make the same mistake I made. All right, next we are going to make, well, I won't mess this one up. Translate the quadrilateral with vertices R, S, T, and U along the vector -3, -3. Now that vector, that means that the horizontal component of the vector is -3, which is to the left 3, and the vertical is -3, which means you will go down 3. So let's write down our coordinates of our points and do the math to change them. So our point R of our pre-image was at 2, 5. So we would subtract 3 from the x-coordinate, subtract 3 from the y-coordinate to get a new point of -1, 2. Our s-coordinate was at 0, 2. That's the pre-image. And our image, you would subtract 3 from both of those to get -3, -1. Our t-coordinate was at 1, -1. So again, we subtract 3 from the x-coordinate, subtract 3 from the y-coordinate to get -2, -4. And finally, our u point coordinate was at 3, 1. And we subtract 3 from each of those to get 0, -2. Now we would graph the pre-image, which is the RSTU, which is purple. And then you would graph the image, which is R prime, S prime, T prime, U prime, which is red. And you can see that we have translated that to the left 3 and down 3. This example is with a recreation kind of problem. We have a sailboat. It has the coordinates 100 degrees west and 5 degrees south. Then the boat sails 50 degrees due west. Then the boat sails 10 degrees due south. So the vector is going west and south, or left and down. What is the boat's final position? What single translation vector moves it from the first position to its final position? All right, let's sketch this out. So the boat's starting coordinates are at -100, because 100 degrees west, we're going to use that as -100, and 5 degrees south, we're going to use -5. So it was 100 degrees west, we're going to use that as -100, and 5 degrees south, we're going to use as -5. So put your original point, and look at our coordinate system. We're going up by 5s on the vertical axis. On the horizontal axis, let's see, how are we marking these? This is -50 right here, and -100 would be right here, and this would be -150. So these are like every 25 units. This would be -75, and so on. So -100, -5 is right here. And then we are moving. And we're moving until it gets to -150, -5, because first it went west. It went 50 degrees west. So now it's right here. And then it went south. And it went south by another 10 degrees. So we move down to here. So our final position then is right here at -150, -15. Now the vector that would move it directly from here to here, rather than having to go first west and then south. So we went first straight west, and then we went straight south, so we ended up here. We could have gone directly there by going -50, these should be pointy brackets, and then -10. Here's another example, but it has to do with the problem in your textbook. So if you want to follow along in the example in your book and then go through this example, you can. And that's it. I hope you learned a lot about translations and using vectors to show the translations. If you have any questions, please let me know.